Hey guys, today I'm going to be doing a tutorial on the Kart-Controller that I've been using in my Mario Kart games. And if you haven't in my Mario Kart game, and if you haven't seen that, you should check it out on my YouTube channel. It's like a whole separate playlist. And today I'm going to be showing you how I created that, and I'm going to be showing you the most important stuff. I'm not going to focus on too many little details. For example, I have no character in my Kart-Controller, but the character doesn't matter. That's just for aesthetic purposes. You just animate a character and put it in. I'm not going to be showing you that, but I'm going to be showing you the actual controller itself. So to start off, let me show you some settings that are specific to this project. It may be different if you're tweaking some things in this tutorial project later on, because I'm going to be putting a link in the description to this project, so you guys can check it out for yourself and play around with it and tweak settings if you want. So the first thing I wanted to show you was that if you go to Edit, Project Settings, if you go into the Physics section, I set the downwards gravity really high. That's because our car is going to be moving fast. So if you want the full effect of the gravity pulling down on you, if you go on ramps and stuff, like the actual Mario Kart games, then you want a higher gravity. And keep in mind that if you're falling from really big heights, then sometimes you might clip through your ground. So that could be a problem, but in this tutorial and in my Mario Kart games, I mean, I don't think there's any course that drops you that high. So I don't think this big gravity should be a problem. So let's get started on the tutorial. So the first thing I wanted to show you was the actual player object. I wanted you to understand the hierarchy over here. Before we get into that, let me just show you what else I have in the scene. So obviously I have a directional light. I have an item box, which we won't need in this tutorial because that's from my previous tutorial. If you want to check it out, just visit my YouTube channel. It should be like, I don't know, 2-3 videos below. There should be 2-3 videos down the latest updated videos. Then I have a plane, just ordinary plane. I have an object over here. Hold on. I have an object right here, which will be the camera following the player. I'll explain that later on. Then I actually have the player object. I just have a canvas, which was also from my previous tutorial. I'm using the same project again, and I'm just adding on to it. So some stuff here you don't even need, so like the canvas, I don't need it. I also have a reflection probe. Now the point of this reflection probe is to give the cart a nice metallic feel, because metal reflects stuff. It reflects around your surroundings. So as you can see, hold on, if I can get here. Oops. Yeah, so see, the cart is very reflective. Combined with the cart's material being very smooth and added a little bit of metallicness to the material as well. So that plus the reflection probe will give you this look. I will be putting this project in the description, so I think I've already said that. Okay, anyways. Then now I also have trees here, the tents for aesthetic purposes, and then the road itself. All of these assets can be found at Kenny. So search up Kenny Racing Assets, you will find them. So let me show you the final product of what this is going to look like. So hold on. So basically, you just press space to accelerate. You can drift. Obviously, this track isn't what you'd usually see in Mario Kart. They'll probably have some better tracks in that game, but this is for demo purposes. As you can see, you get a boost. You can go on the bridge, and here's the gravity being in effect. Bumpy surfaces. You can get more boost if you keep trying. I didn't add mesh colliders on everything, so you can just clip through some things. And the higher the stage of the boost, the longer of the drift, the better boost you get. So this is basically what I'm gonna be showing you. I'm not gonna be making it from scratch because that's gonna take a while, because I make mistakes sometimes, and trial and error will make this a long tutorial. So I'm just gonna be showing you what I created here, and I'll be showing you the programming as well. I think you guys saw enough. So now let's go into the player object. So here you have the main player object, which has all the player scripts in it. the sphere collider. And by the way, I'm using a sphere collider. This is a simple approach to a kart controller. It's not something complex like you would see in the actual Mario Kart game, but it does the job to my expectations. And I also have a rigid body here, simple stuff. Now, this is the second child object, or this is the first item in the hierarchy, which is in the child objects of the main cart. And this has an animator on it, as well as a small script full of utility functions, very small functions that I felt like you don't need a whole script for that one function. So I bunched them all together in a script called utility functions. I'll get to that. So basically, what I have here is a hop animation. Obviously, it's not going to be looping like this, but when you drift, you'll always get a hop, and this animation will play. And it also has, and the animator is just a single animation here, just hop. That's it. Alright, then moving on. I also have another hierarchy object. This is because in my actual Mario Kart game, I had lots of animations, such as when you can do tricks off of ramps, or when you get hit by a shell, the cart flips and all that, and all those animations will be placed over here, and the hop animation was placed over here. So I tried to mimic exactly what I did in my actual Mario Kart project, which is why the hierarchy is pretty big. So anyways, so further down, here's the actual model of the cart. Yeah, that's pretty much the chassis. And then I also have the particle effects here, 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 and here. These are all particles, which I'll get to later. Well, let me just play them for you. So this is the explosion of the boost. So every time if you had a golden mushroom, you keep spamming it. Every time you press a button, this particle will play. As you can see, it's like a simple burst. And then the actual flames would be right here, as you can see. These flames would also be playing at the same time as the bursts, but the bursts will only play once, and this would keep looping. And now the thing I wanted to explain to you guys was the tires, because the tires are really important. As you can see, the front left, front right, back left, back right. And the front tires are the most complicated ones because you have to steer and spin at the same time, right? So the outer portion of these tires, okay, so if you go down each one, the front and left and front right tires are the same thing, so I'm just going to show you the front left. There's a hierarchy of 3 objects, as you can see. I know it's pretty, I think there's obviously going to be a better way to do this, but this is a really easy way to follow it, because the parent object is going to be rotating left, right to steer. It's not the most realistic steering, but it works because no one's going to look at the wheels from this angle. So that's steering left and right. And then the middle object, or the child object, is the one that's going to be spinning on its local axes. As you can see, that would give the effect of the tires spinning. And the model is right here, but the reason I have this huge hierarchy is because, as you can see, the model and its pivot are not the model's pivot is not in the center of the actual wheel. It's somewhere out there, right? So we can't really rotate this to give the spinning effect, because that's going to give some weird rotation, right? That's not how wheels spin. I don't think that's how wheels spin, right? So you take your parent object and make sure, I can't emphasize this enough, make sure the pivot of the parent object is directly in the center of your model. If it's not, move your child model or your child object around a little bit and make sure that pivot's in the center. In my case, it's already in the center. So when you rotate it, you get a clean rotation. And then make sure for your main parent object of the tire, it's also in the center this way, because it's going to be rotating left and right. And you want a proper tire rotation, right? So you want to make sure it's in the center, left to right. It doesn't have to be in the center, up and down. Doesn't really matter about that. It just matters, it has to be in the center, left to right. And then let's go to the back tires. So the back left tire, same thing, but it's pretty simple because these ones don't steer. So it's just a model and a parent object. Again, with the parent object, the pivot's not in the center, so I had to give it a parent object and rotate that instead. Here, as you can see, the pivot's in the center, so you get a mostly clean rotation. You can't really tell that it's not perfectly in the center, but try to get as perfectly to the center as possible, so you can get a nice rotation. But yeah, so that's what I wanted to show you in the cart model. So now let's get into the actual script. So let's let this open. It might be a little bit slow because I'm using my laptop. I don't have an actual computer, but it does a job. Anyways, here I have many functions. Basically, they're all in fixed update, and these functions do everything that you just saw in the preview I showed you in the beginning of the project. So I'm going to comment most of these functions out except for the move one, so I can show you what it does, and then I'll get to explaining the script or the actual function itself, the code in the function. So yeah, so here's what the move function does. It just makes you move forwards and backwards. If I press S, it goes backwards, and press space, it goes forwards. As you can see, there's no tire movement, steering, turning, or anything, just moving back and forth. So let me explain how the function works. So I folded up all these functions over here. So I'm going to open the move function by pressing this little plus button over here. And here's the function itself. So right off the bat, actually, hold on, let me show you the variables that you're going to need for this function. So there's 4 variables. There's current speed, which is a speed that you're currently applying to the rigid body. The maximum speed that you're allowed to go to. The boost speed. The boost speed is actually not really required in this function specifically, but I'm just going to show it to you for later on. And then the real speed. The reason I have a real speed and a current speed is because when you apply the current speed, you can't really check the velocity and get an accurate representation of what the velocity is. Say if I'm running into a wall, if I'm trying to drive into a wall, and I want to check the velocity to see if it's, well, if I'm moving slow or fast, because if you're bumping into a wall, you're not really moving. But then if I check the velocity, it's still going to show you the velocity of the maximum speed, for example. Say if I'm applying a velocity of 60, then if I check the velocity, it's still going to show 60, even if I'm not moving and I'm bumping into a wall. This is because I'm applying this variable as the cart's velocity. So every time I check the velocity, whatever current speed is, that's what the velocity will return. So to solve that problem, you have another variable called real speed, and before you set the velocity of the cart with current speed, you check what the velocity is and set it to real speed before you set it. So you check it and then you set it. So basically, real speed can be used as a reference for any other special effect. For example, in my game, I had Mario's hair moving, but for that, I want to have the real speed, right? Not like the current speed. Because say if I'm running into a wall, I don't want Mario's hair waving and moving around, even though I'm not moving, right? So you want the real speed, not the applied speed, okay? So let me show you, okay? So in real speed, what we want to do is just do real speed is equal to transform.inverse transform direction, rigid body dot velocity dot z. So what this does is it gets the local. Because if I go into the player object, right? If I set the transform to global, if I rotate the cart, the blue axis always points that direction. But if I turn it to local, the blue axis follows the cart's forward direction. So this is how you get. So this line of code is how you get the local direction of the cart. Then you plug in the rigid body's velocity, and you get the z component out of that, which is the actual velocity of the car moving forward. Then, and this is all before we set the velocity over here. This is why real speed is an accurate speed, and current speed is the speed that we're applying to the car to make it move. So usually you want to use real speed if you want reference. So okay, anyways. So if you press the space key, the current speed is getting increased, obviously. And then after all of these, after setting current speed over here, we basically apply the current speed to the velocity, or a vector 3, and then we apply that vector 3 to the rigid body velocity. So let me explain all of this first. So what we're doing is we're lerping the current speed with mathf.lerp, and we're kind of interpolating whatever current speed is right now, and we're trying to increase it gradually towards max speed. And this is the interpolation speed right here, times that delta time, multiplied by 0.5. Now if we press the S key, which is reverse, we want to interpolate current speed to this value right here, which is negative max speed divided by 1.75. Because I don't think a car can reverse as fast as it can accelerate forward. So we just divide it by some value, and this is how fast the car can reverse. And we're interpolating the current speed to this value over here, and the interpolation speed is 1 times time dot delta time. And if we're not reversing or accelerating, we gradually want to slow down, so we're interpolating the current speed to 0 over here with an interpolation speed of 1.5 times time dot delta time. Now, once we have our current speed variable ready, we just create a vector 3, call it vel or whatever you want. We do transform that forward, which is the forward direction of the car in local space, and you multiply it by current speed. Now, what we also want to do is add velocity.y is equal to rigid body.velocity.y. Because if we don't add this line of code, gravity will play little effect in the actual the cart's movements. So we want to leave the y velocity alone and just tamper with the x and z velocities, not the y. The y is controlled by gravity, so we don't have anything to do with that. And then we finally apply the rigid body velocity. We put vel in the, we just set vel to the rigid body's velocity. Or we set rigid body's velocity to vel. That's what I meant to say. So now you already saw what the move function does. So I'm going to comment out the tire steer, and I'm going to explain what the tire steer does, that function. Obviously, I'm pretty sure you can already tell it just controls the tires. If I'm pressing left and right now to steer, but since I didn't enable the steering function, the car is not going to turn, but the wheels spin according to the speed you're going to. So let me show you how I did this. So if I'm going to close this function because you guys already saw it. The tire steer function, what I'm doing is if I press the left key, I'm changing the front left tires local, I'm not sure how to say this, Euler angles, whatever. The front left tires local Euler angles, and also the front right tires local Euler angles. And since the default angle it has is, let's check it out, I think it should be 180. Yep, as you can see, the default angle on the y-axis is 180. If we turn left, or say if we turn left, we decrease that by 25 degrees. So it turns 180 minus 25 is 155. And as mentioned before, we use a lerp function, but this time it's a vector 3.lerp, not a mathf.lerp, because we're lerping a vector 3. So we're lerping the current Euler angles of the tire to this vector 3 over here, so we can smoothly interpolate it with this interpolation speed right here. We do it with the right and the left tires. And also, same thing as for turning left, we do it with turning right. It's pretty self-explanatory. And now, if we're not pressing left or right, we just reset the angle, which is 180. The reason I'm doing 180 is because Euler angles never go to the negatives, and 180 is basically the same thing as 0 because they're just opposite to each other. So I can just set 180 right here, and it should be good to go. Because 180 is directly opposite to 0, so it's opposite, but like the rotation is pretty much the same, if you know what I mean. For tires, in tires it's the same. So now here's a tire spinning, okay? So I did a little refinement here. You don't have to do it, but what I did here was that for if the current speed is greater than 30, then I just rotate the tires, the front left and front right child object. I just rotate that object at a speed of -90 times time dot delta time times current speed times 0.5 f. So I just did a lot of experimentation. I got this value here. So I rotated it with the speed of this value. And since I'm multiplying by current speed, the wheel's rotation will always be in sync with the tire's rotation. But since this is current speed that is greater than 30, then the player's not really going to visually see if the tire's speed, rotated speed is accurate with the movement. You can't really tell because this 30, the tires will be moving so fast you can't even tell. So to make it more accurate, if the speed is less than 30, well, if it's less than or equal to 30, we use the real speed. Because the issue I got was if I move, sometimes when I go really slow and I slow down, if I wasn't using real speed, then the tires would just kind of rotate a little bit longer, because the current speed is still kind of like not quite there at 0, but almost there at 0. So even if the cart has visually stopped to the player, the tires would kind of still rotate a little bit more. So if the speed is less than 30, I use real speed. If it's more, I use current speed. And the back tires, since there's only one child object, I just rotate the main object for the tires. Since there's no child object, I can't really do anything with it. So tires, the back tires are just spinning, so I can use the main parent. But as you can see in this, in the front tires, I have to use the get child. I have to use front right tire dot get child 0, which is the index of the child object. So basically, what I'm doing with get child 0 is accessing this object and accessing this object. So I'm spinning these objects and rotating these objects while steering. And this is for, well, speed and spinning and whatever. You guys understand, right? I hope I didn't confuse anyone. So that's tire steer. So now I'm going to uncomment steer. So obviously steering, actually I'm not even going to show you because steering is pretty self-explanatory. Just steer while you move. So I'm going to explain the steer function now. So basically what I'm doing is I'm getting a float value which is determined by your input, and it's called steer direction. And now I'm using input.getAxisRaw, which can work with left and right arrows or the A and D keys. Same thing, because you need these configured by default with the A and D keys or left and right keys for the horizontal axis. Okay. So I'm also creating this vector called steer directional vector, steer direct. That's what I just called it. And after doing a lot of code over here, we finalize this this vector, and we rotate the cart, which gives the steering effect. Because what we're doing is, as we're moving, we're kind of rotating the main cart object. Hold on. As we are moving, we're rotating the object, so the cart moves in a different direction while it's moving forward. So it gives the effect of steering. It's not obviously not real steering, but it works for the game, and you won't notice it. Trust me. So basically what we're doing, ignore this drift left and drift right and all that kind of stuff. Basically what we're doing here is we're adjusting the steering strength while we're drifting, but I'll get to that when we come back to the drift function. So here we also have a float called steer amount, and what we're doing is steer amount is equal to real speed. Well, first of all, this is basically an if-else statement condensed into a ternary expression. So what we're checking here is real speed greater than 30? If it is, then the steer amount is going to be real speed divided by 4 times steer direction. If it's less than or equal to 30, then we're going to do steer amount is equal to real speed divided by 1.5 times steer direction. Steer direction is going to be 1 or -1. So -1 is going to be the opposite of 1. So if we multiply it by a negative number, it just becomes that number, but a negative version of it. So it's going to be the same. So the reason I'm doing real speed divided by 4 and real speed divided by 1.5 is because when you're making a cart, the steering strength will be obviously stronger when you're moving slower than when you're actually driving really fast. Because think about it in real life. If you're steering, what's going to be easier to turn if your speed is slower or if you're moving really fast? Obviously, it's going to be easier to turn if your speed is slower. So I have these two. I have this if-else statement to determine the steering strength. Obviously, it's not the smoothest thing in the world. In my actual Mario Kart game, I didn't use the if-else statement. I used a bunch of else-if statements to minimize the choppiness inside that. Because as you can see, if I accelerate, I don't know if you saw that, but let me just go on the graph so I can show you. When I'm steering from the speed of 0, I'm not sure if you caught that, but it was like a choppy steering thing that just happened right there. So to avoid that, you can use multiple if statements, but for the sake of this tutorial, I'm just using an if-else statement, so 2 things. And finally, we make the steer directional vector equal to new vector 3. We don't want to modify the x or z or Euler angles. We just want to modify the y because we're rotating the cart, right? So we're just rotating the cart's y rotation, or we're adding steer amount to the cart's y rotation. And then transform the Euler angles. Now we're setting the Euler angles equals to vector3.lerp, so what the kart's current rotation is, and then we're trying to approach the steer directional vector at a speed of 3 times time.delta time. So we're basically making a vector3, and then we're trying to set the rotation of the kart to that vector3, but we're kind of smoothly interpolating towards it. So now let's go into the ground normal rotation. If I click play and play through the course, if I go quickly to the ramp area over here, watch this. If I don't enable the ground normal rotation, the kart just looks like, like it's floating on the road and just going up like that. We don't want that. We want the kart to actually rotate along the ground, right? That's what real cars do. The wheels make it, rotate toward the parallel to the ground. So what we do here, we have a raycast. We shoot a raycast downwards, as indicated by the negative transform dot up, and then if it hits something at a distance of 0.75 units downwards, then we basically, this line of code, I'm just going to leave it up so you guys can copy it down. I actually got this from a Unity forum, and basically what we're doing is our rotation is going to equal to the rotation of the ground normal. So, and then we also have this boolean called touching ground is equal to true, because 0.75 is awfully close distance from the kart to the ground, so it's almost like as if you're touching the ground. So I'm just going to have this boolean here. We're going to be using it in the drift function, so this is why it's important. Otherwise, if you don't hit a raycast at a distance of 0.75 units downwards, then touching ground is false, because then you're obviously not really near the ground, so you're not touching it. So whatever is depending on this boolean function does not work. So obviously, if I enable this function, now I can rotate along the ground. So let me show you. Yep. As you can see, now we're rotating parallel to the ground. And the reason I had that touching ground thing over there was that you only rotate along the ground if you're that distance close to the ground. So watch this. You can even jump off the ramp. Well, not now, but hold on. Hope I can get this. So I'm just going to move a little bit back so I can get a really good speed. And you can watch me jump off the ramp. So I don't know if you caught that, but say if you're not really that close to the ground, you don't rotate parallel to the ground to give the effect of a jump, like how real physics would act like. So that's why I have this 0.75 thing here. But anyways, let's continue on with the tutorial. So now I have the actual drift function. So the first portion of the drift function is if you're pressing down the V key and you're actually touching the ground, then I play the hop animation of the child object of the main kart. That's why I say get child 0. You can keep pausing the video if you want to see the code, because this video would be awfully long if I really in-depth explained each line of code. So the steer direction, which is actually a boolean declared in like in the actual class right here, which is accessible by any function. So steer direction, and I actually set the steer direction in the steer function right here, steer direction. So we don't need to reset it, set it again in this function too. So basically, if we're steering to the right, if steer direction is greater than 0, drift right is equal to true, drift left is equal to false, and these are all variables declared in the class up there. So any function can access it. And if steer direction is less than 0, then drift right is equal to false, and drift left is equal to true. If it's equal to 0, then the booleans will be will by default be false, so nothing's going to happen. So now that's what happens as soon as you press V to drift. Now, while we're drifting, because it says input.getKey, so while we're pressing the V key and touching the ground, and the current speed is greater than 40, because you can't drift if you're moving really slowly, and our input.getAxis horizontal is not 0, so if we're not pressing so while we are holding a left or the right arrow key, and if we let go of both of them, in like half a second the drift will stop, because well then the input.getAxis horizontal will equal to 0. So we have this variable called drift time, and we're increasing it by the time that we're drifting. And these are the sparks and the particles for the effect for the spark. So basically, what we have here is I is less. So we have a for loop here because, as you can see, if I show you here, the drift particles, the main drift particle object has 5 different particle systems in it to give you a really good effect of a drift, right? So what we're doing is, for every child object of the drift particle systems, in this case, since both left and right wheel particle systems have the same amount of children, then we can just do dot child count of any of them. So I'm just going to do left drift for now. Then what we're doing, we have the particle system, we have a reference to the particle system, is equal to right drift dot transform dot get child I. So we're basically getting the child object, the ith child object of the main parent particle system, and we're getting the particle system component of it. So this is the right wheel, and this code is the left wheel. So now we want to access the main module of that particle system, which is like the main component of it. See, all these settings belong to the main module of the particle system. So we want to have a reference to that. Same with the left wheel particles. They're both these things are both the same, each one for left and right wheels. Then what you want to do is we want to set the start color of both of these main modules to a predefined color. So if I go into the actual inspector and go into the player object, it's just recompiling the script. So I have 3 colors. Drift 1 is a light blue color, Drift 2 is an orangish yellowish color, Drift 3 is like a purple color. So these are the colors representing the different drift durations. So if the drift time is greater than or equal to 1.5 but less than 4 seconds, then we want to set the color to drift 1. And if the particles are not, and this code checks if the particles are playing. If the particles are not playing, then we play them because we want them to continue playing while the drift is going. Okay? So now that's that. So let's go into this one. So what we're doing is same thing over here. All we're doing is getting the main modules of the particle systems inside the child objects inside the main parent object, right? Because there's 5 particle systems. With the for loop, we're accessing each one, getting the main module of it, and then we're setting the start color to drift 2 if the drift time is greater than or equal to 4 and less than 7. So it's pretty much the same as the other function, but it's just for different times we have different colors, right? And then finally, if drift time is greater than or equal to 7, we get the main module components of the particle system, set the color to drift 3, which is the purple one, and that's pretty much it. Now, actually, that's pretty much all of the while you're drifting function if statement. So that's that. And this function, well, I mean, they're not really functions, they're just if statements, but this if statement controls if you're not pressing the V key or if real speed goes below 40. So you stop drifting if your real speed goes below 40 or you're not pressing the V key, right? So obviously drift left is false, drift right is false, and this is a boolean which I'll get to later. And depending on the drift time, I set the boost time. So basically over here, if drift time is greater than 7, the boost time should be like 2.5 or maybe 3 seconds. I don't know how long it really is. This is an estimation. If it's like a yellow or orange boost, right, like in the real Mario Kart game, the boost time should be like 1.5 seconds. If it's just a mini turbo or the blue one, it should be 0.75 seconds. So that's pretty much what that does. And while I say the boost time, right, there's this function called boosts. And this function is always being called in fixed update, just like every other function. And we're constantly subtracting time from this float value. So this would, if you never drift at all in this game, this would be a very negative number, but whatever. If boost time is greater than 0, since we set it here, all these numbers are greater than 0. If it is greater than 0, that means you have a boost. And if you have a boost, then we play all the particle systems. What we're doing is the fire particle systems, as you can see right here, the fire. So hold on, it's right here somewhere. Yeah, right here, boost fire. So we have a reference to 2 of these, all of these flames, right? So we have a reference to these flames, and they're just one particle system. But we don't have a reference to this in the actual inspector. We have a reference to this. So the child objects are the particle systems. So we're just getting the particle system component of both of those child objects, and we play it if the particle systems are not playing, because we don't want to keep playing the particle systems over and over again, especially in update, because that will basically like take up so much performance because it keeps on playing the particle systems 60 times a second, and you only want to play the particle system when it's not playing, so it just keeps on going. So if the particle system is not playing, then we play it, and then we also set the maximum speed to the boost speed, which should be 20 more. So the maximum speed usually without any effect is 60, and then the boost speed is 80. So while you have a boost, the maximum speed becomes 80. And we also add another lerp statement over here to make you reach the boost speed faster, because the other lerp statement in the move function would also take you to the boost speed, but it'll do it a lot slower. So if you have two lerp functions, it'll take you there a lot faster. And if you don't have a boost, we just set the maximum speed to, in this case, 60, because 80 minus 20 is 60, which is a normal speed, right? And so that's what we're setting our maximum speed to. And also, we stop the flame particles from playing, because there's no boost, so why should you play flames? So that's the boost function. We already saw the tire steer function, and we saw the drift function. So that pretty much covers all the functions in the player controller script. And if I uncomment all of these functions in the update, once again this is what it gives us. And there's one more thing that really covers the drift function, is in the steer function. As I mentioned before, all of this code over here kind of like gives the effect of an actual drift. So what we're doing is we have a steer direction, right? It's initially 1 or -1 or 0, right? And if we're not drifting, all of this code gets skipped and it goes directly here, right? But if we are drifting, if we're drifting left, right? What we want to do is we want to increase or decrease the steer direction depending on which way we are drifting. Say if we're drifting left, right, and not right, if the input.getAxis horizontal is less than 0, so if we're pressing the left key, then we want to set the drift strength or the steer direction strength to -1.5, and if we're pressing right, or we're not pressing anything at all, then we want to set it to -0.5, because if you're drifting leftwards, there's no way you can turn right because you're drifting leftward. So the only thing you can do while you're drifting left is control the strength of your drift. You can either drift sharper or you can drift a little bit weaker, but you're always going to be steering to the left direction, right? And I also have a Boolean condition here. If you're close to the ground and you're sliding, and I'll let you know how I got this sliding variable working, since that was not in any of these functions over here. So if you're sliding, then we add a force in the opposite direction of the drift, which would be, in this case, transform the right. Because if you're drifting towards the left, then to get the effect of a centripetal force, you would add a force to this direction, so you can actually get effect of drift. So because if this statement was not here, your drift would look like this, as you can follow my cursor, like a sharp turn, right? But if you have this function, it would be like this, which will give you a nice drift, right? So that's why we have a add force statement here. It gives you a force, and the outwards drift force is just the acceleration force I'm adding here, and the actual value of it is I think I said it here somewhere. Probably like it's around 50,000. I know it's an acceleration force, and in this specific project, after experimenting, it was a force that felt right to me. If I actually comment this code out, you'll see the drift is very unrealistic, and it just looks very bad. And actually, I think I messed something up with the comments here. It's an if statement, so I'm not gonna comment it out. But actually, let me just comment it out. And okay, so I'm just gonna do a left drift. I'm just gonna comment out the left drift. And this is the right. I'm just gonna drift to the right, so I can. This is what it originally looks like, right? You're just sliding towards the outward side of the track. But if I drift leftwards, it's just basically a sharp turn. I don't really think a drift is a sharp turn, right? I think it's like you're actually sliding on the ground. So you actually want this if statement here and the add force over here, so it gives the effect of a drift. Now, to cover how I got this is sliding boolean working, we have to go into the animation of the hop. So when you drift in Mario Kart, you actually start sliding when the cart bounces up, and actually when it touches the ground, that's when you start sliding. As you can see, this is the animation. So when you bump back into the ground, I have this event over here, and since this the animated object of the hop has utility functions here, I have an event which calls the set drifting function inside utility functions. So if I actually open up utility functions, all I'm doing is getting the parent object of this, which is the main player object with the player script on it. I get the player script component and set the boolean is sliding to true, because we don't want to add the force of the sliding force right when we are hopping, because that's not really realistic. The sliding force should only happen when you drop back to the ground, right? So that's why I have the is sliding variable, which turns true as soon as we come back to the ground in the animation. And back to the player script, in the drift function, well, when we're not drifting anymore, I also set is sliding to false, because we don't want to slide on and on while we're not even drifting, right? So basically that's basically the player script, and you already saw how how everything works. So it's just moving left and right. And by the way, in the actual Mario Kart game, the steering wheel doesn't even move because it's part of the actual kart itself. It's just you can't see the steering wheel because Mario's big hands are getting in the way. But yeah, that's pretty much the kart controller. And I'm going to be showing you the camera follow, which is this player look at thing. So basically, the player look at is just an object, empty object, with a script on it, and this object is what is actually following with the player. So how this works is that this object, which actually has a camera, right in it's a child object of that player look at object, and it's inside that object, but it's somewhere in the back. So basically, what this is doing is this main parent object of the camera is always following is at the exact same position as the cart all the time, plus this offset, which is just a +2 in the y position of the cart, and it's always at that position, right? And since the camera is at the back, the camera always follows the parent object's movements, as you can see here. The camera always follows where the parent object is going, because it's part of the parent object. So the rotation, that's another story. How this works is that this player look at object gradually rotates to the direction the cart is rotating to. If it did not gradually rotate, you would just get a choppy rotation. And if you see in the game view, as you can see when I'm turning, you can kind of see the side of the car, right? And especially when I drift, right, you can see the side of the car. But if the camera was never slowly interpolating, then you would never really see the side of the car. The only view you would ever get of the car during the game is this back view, because the camera would directly be following the back of the car all of the time. But since it's a gradual rotation, it gives you the effect of the actual Mario Kart camera. So let me show you the camera follow script. So we have a vector 3 called offset. We have an access or a reference to the player. We also have a reference to the player script. And we have two other vector 3s which control the child object or the camera's position, or this object specifically, not this one, but the child object, which is actually the camera. These two vector 3s control its position. or its local position. So we just get the player script in the start function, and then what we do to make the player look at this object, follow the player at all times, we just do player.position plus offset. So we just set the position right here. And to slowly interpolate the rotation, what we do is transform that rotation is equal to quaternion.slurp, transform that rotation, so what it is right now. And we're approaching the player's rotation with an interpolation speed of 3 times time.delta time. Now here's where it gets interesting. You may recall that when we play a game and we get a boost, right? The camera moves slightly back. But it's not the actual player look at object that's moving back. It's the camera child object which is moving back and moving back to normal when you're not having a boost. So as you can see, it moves forwards and backwards to give the effect that the cart is moving really fast. So to transform that getChild0 to our local position is equal to vector3.lerp, what its current position, and then the boost camera position, 3 times time.delta time, which is the interpolation speed. And this is because this we check if the player script at boost time, so if the boost time in the player script is greater than 0, then we lerp the position of the camera to the boost camera position. Otherwise, we're not having a boost, then we just lerp it to the original camera position, which is what it is right now. And I actually set these variables right here in the inspector, so you can tweak them if you don't like them. So that's pretty much it. I mean, that's the Kart-Controller tutorial. That's the basic skeleton of what's in there. Obviously you might have noticed some flaws, like how between these two wheels there's no axle, and the axle can just be placed with a simple cylinder in between over here. Nothing special about that. The steering wheel doesn't move because it's part of the actual cart, so you don't really need to do that because Mario's big fat hands will always be blocking it, so you can't really see it. And yeah, so that's pretty much it. I hope you guys understood everything. I hope you guys liked the tutorial. If you guys liked it, please leave a like, and if there's anything else that I might have missed or you guys want to know, you can leave a comment in the description, because I'll be more than happy to help in the comments for anything extra that I may not have covered in this tutorial, or if you have any more questions, okay? And the next video will either be a progress video of my Mario Kart game, or just another tutorial on the character controller I used in my Super Mario 3D World game. This is all a request. This cart controller was also a request. Oops, okay, that was a little weird. So another thing you can do to avoid this glitch that you see right here is just adjust the normals, go into the ground normal rotation script, and you can search this up on the Unity docs itself. I did wrong script. This is from another project actually. I don't know why it's in here. You can actually go into the Unity docs and see how the raycast detects the ground normal. So if your ground normal is beyond a certain point, say if the ground is too steep, then you don't rotate past that rotation. You know what I mean? So if the ground is too steep, you don't rotate past that. So you can avoid that glitch you might have just saw there. And anyways, I was saying that this tutorial was a request by a few people that have watched my Mario Kart videos. So I did a tutorial because I thought, okay, so if this many people want to see a tutorial, why not make one? And another tutorial request was the actual 3D World character controller that I created in my other game. So that either that will be my next video, or just a progress video on the Mario Kart game. And yeah, thanks for watching, guys. This is pretty much it. Let me know if you have any questions in the comments section. Thanks for watching. Bye. So there was one more thing I wanted to show you guys before I end this tutorial, and I completely forgot, but let's get on with it. So the one thing I wanted to show you was the gliding part. So as you might have seen, if you see my Mario Kart game, you know there's gliding in that, so I'm going to show you how I implemented that. And also, here's what it actually looks like before I actually go ahead with the code. So I'm just going up to this ramp, and it's going to be a blue thing, which is a glider ramp. And then here's what it looks like, the gliding. And obviously you have more control. And obviously, the more if I press the down key, I go up, and I can if I press the up key, I can move down, and left and right obviously just steers. And that's pretty much it. So let's get on with the code. Let me show you one more time before we continue, which is just right here. Alright, that's pretty much it. So let's check it out now. Alright, so if I open the player script, I'll close Visual Studio Code, so it might take a while to open again. Alright. Okay, so there's a few things that I've added. Well, first of all, let me show you the glider panel, which is what you need to actually start gliding. So this is a little odd, but it has two box colliders on it. One is actually the collider for the actual cube. This is not the important part. The important part is this box collider, which is trigger, and which is placed directly on top of the glider panel, as you can see here. And once the player exits this collider after entering, then the glider opens and you start gliding. So, and I give this a tag of glider panel. One thing you guys should also note is the grass over here has a tag of off-road, and all these road segments have a tag of ground. Okay, so you might want to keep that in mind when I show you the code. So let's go into the code now. Oh, and also one more thing. In the model of the car, in the cart actually, inside the second child object, I have a glider over here. I know it's a Blender model, and all the animations. Hold on, all the animations and materials and everything is right here. And this project is going to be in the description anyways, so you guys can have all of this if you want to check it out for yourself. But I'm not going to go too much in depth. There's two animations on it. The main parent object has the animation of unfold, so it's basically coming up and unfolding. And then the other one, well, for the folded animation, it's just not really an animation, it's just a state. So as you can see, it's inside the cart, so you can't really see it when you're playing the game. And there's another animation, which is glider close, which is basically the same thing as open, but the opposite. So it shrinks that way and it closes. And there's also wind flap, which is a Blender animation I imported, since this is a Blender file, which is basically just the glider going against the wind. So just to give the effect of that. And that's pretty much the glider itself. So let's go into the actual code now. So the first thing you want to know is this on-trigger exit, which wasn't here before. What it checks for is that is a trigger that you exited does the trigger that you just exited have a tag of glider panel? And if it does, then you set this variable glider fly, which I declared right over here, and you can tell it's an important variable because, well, it's in all caps. It's not the right convention, but I like to do it like that to make sure, or keep as a note to myself, that this is a very important variable. So glider fly is true. Then I go into the animator and set this variable to true, which opens the glider, and this variable to false, which is later used when closing the glider. But right now we're not closing the glider, so I just set this variable, or this boolean inside the animator, to false. And now I have another on collision enter here, and this time you're checking if you collided with the ground or the off-road section. Remember I described those tags to you? Well, these two things are basically the entire ground that the cart's driving on. So now if you collide with that, obviously your gliding has ended because you're on the ground. So glider fly is false. I basically do the opposite of what I did here. I set this one to false and this one to true. Same thing over here. I mean, that's basically what I did over here. Glider open to false and glider close to true. If you want, I can show you the animator right now real quick. It's just a cycle. So the folded is the default state, then it goes to unfold, then it goes to glider close, and then after it's closed, it's in the same state as this. Basically, the end of this animation is the same as this whole entire state, right? So I just go back here. Um, yeah. So let me start describing what this boolean is used for, and let me check if I put it in, if I added it in move. Yeah, okay, there you go. The first thing that I added was this section of code right over here, this segment of code. So if you're not gliding, as you can see by the exclamation mark, then it just behaves normally. Velocity.y is equal to rigid body.velocity.y, which is the gravity. And now here's the gravity with gliding. And as you can see, it's almost the same. However, what I did was velocity.y is equal to rigid body.velocity.y multiplied by 0.6. Now what this does is it takes the y gravity, the y vector of the gravity, and reduces it. It kind of like shrinks it. And now if we apply that, if we apply the vector to rigid body velocity, the gravity will be way weaker because I multiply it by 0.6, which gives the effect of floating while you're gliding. Because when you're gliding, you don't fall the same speed. You don't fall to the ground at the same speed as when you're actually driving, if that makes sense. The second change I made was in the steer function, and this is a big change, okay? So all this stuff is basically the same as last time, but over here is what I changed, the glider movements, okay? So it's all folded up code right now, but basically when you're gliding, when you steer left, you're not rotating on your y-axis that much, but instead you're rotating on your z-axis. Like pretend, like if you saw me gliding right before I started this section of the tutorial, when the player steers, he doesn't steer, the player doesn't steer like this, right? In the sky? No. It steers like this. Like, when you're gliding, it gives the effect of gliding. That's how the player steers. So I'm just going to look at one of these to give you guys an example. So let's say he's steering left. So if input.get key code.left arrow, so if you're steering leftwards, and you have to make sure you're flying, that you're not on the ground, and if it's glider fly is true, so if you're pressing left arrow and glider fly is true, then we have an angle. We have a float angle, which is the local Euler angles on the z-axis of your cart. And now since Euler angles don't really go below 0, and say if your cart has a negative z rotation, well, Euler angles never go below 0, so we have to do some conversion over here to get a negative value. So basically, because the Euler angles, they wrap around after they go below 0 to negative. They don't go to negatives, but if they go below 0, then it goes all the way back to 359, and it wraps around again and again. So this code basically up to a point of a negative 179 degrees, it gives you a negative value for angle, or a positive value for up to 179 or 180. I'm not exactly sure. But I actually found this on a Unity forum. It was about negative Euler angles, and this actually helped me a lot. As you can see, well, it should not be X, it should be Z rotation, but it gives you I put a comment which gives you an explanation of what this does. So basically what we're doing is if angle is less than 40, because if you look at the player, when you're rotating to the left, sorry, wrong axis. If you're rotating to the left, the rotation on the z-axis, local rotation is positive. And I don't think it should be like that, but in this case it is. And if you rotate to the right, then the z rotation is negative. So if we're rotating to the left, we want to check if our rotation or our angle is already less than 40, because we don't want to go past 40. If it is, then we just rotate we have a smooth rotation from the current rotation to the desired rotation, which is basically whatever it already is on the x-axis, whatever already is on the y-axis, but 40 on the z-axis. And so whenever we turn left, our cart rotates on its z-axis to 40. from whatever it is at that point at an interpolation speed of 2 times time at delta time. And I'm using slurp unclamped. And same thing for the right, but instead of the actually, to be honest, now I realize this is not really that important because either way, you're only lerping your rotation to the z-axis on 40 anyhow, so it's not really gonna go past that in the first place. So we don't need this if angle is less than 40, because our cart's already gonna be rotating to this rotation anyways. So basically, what we're doing, we're getting our angle. We don't even need this angle, to be honest, but I'll just leave it in there for now. Hold on, I'm just gonna put a comment here. May not be required. Okay, anyways, because you're already transforming a quaternion to a Euler angle, and then you're interpolating towards that anyways. So I don't think you need this angle variable anyways. So I'll just comment these out. Not required. Anyways, so that's what I hope you understand what the right and left rotation does. Now let's go into this else statement, which is basically if you're not pressing the left or right key, just put the rotation back at 0 because we don't want to tilt left the whole time even if we're not pressing anything. So if you're not pressing anything, slowly go back to 0, a rotation of 0 on the z-axis. Now this is for move. Now let's go on to the moving up and down. Okay, so say if we're in this code and we want to move down, right? Because if you move down, the glider will obviously point towards the ground. Your cart will point towards the ground, and it'll go there faster than gravity pulls it. So what we want to do is, I don't think we need this. I'm just gonna comment it out and remove this because we're interpolating towards this angle anyway, so it doesn't matter. But anyways, what we're doing is we're just rotating. Instead of the z-axis this time, we're doing the x-axis. So we're rotating to an angle of 25 on the x-axis, on the x local axis. And we're also adding a force of 8,000 times time to delta time in the vector 3 down direction, so the down direction. And it's a force, it's an acceleration force. So that's moving down, okay? And otherwise, if you're pressing the down arrow, which means to go up, because if you press the down arrow, you should be going up, like a real airplane controller or a glider controller. If you press up, you should be going down. I hope that makes sense to you, but this is what Mario Kart, how the joystick actually works in Mario Kart. So, anyways, I'm gonna be commenting this out as well. Actually, I'm just gonna remove this. Comment that out. We don't need that anymore. This is all. I just created this code in a hurry. So it may be messy a little bit, but I'm now realizing that you don't need some code in here. So I'll go ahead and remove that once I'm done with this tutorial. But anyways, here, if you're rotating upwards, you want to have a negative x rotation. As you can see, once this recompiles, there you go. So if you have a negative x rotation, you're kind of rotating upwards. So we want to rotate to an angle of negative 25 if the down key is held continuously. And we're also adding an upwards force of 4,000. Because if you're pointing upwards, you're going upwards with your glider, then an upward force would make sense. But you should only use this upwards rotating functionality and this section of the code. You should only use this if you have special triggers around the track which disable this functionality at some point, or the player will just be able to fly around the whole track instead of actually driving. Because in Mario Kart you can't really glide around the whole track. So maybe at some point you would have some trigger which the player enters, and then this flying upwards does not work anymore because you want to stay on the ground at some point. You don't want to stay gliding the whole time. And if you're not going up or down, then the rotation just on the x-axis just slurp unclamped. Okay, I messed it up. So it just rotates or interpolates towards the axis angle of 0, we just leave these two as is. We don't mess with those, and this is 0. If again we're doing this if we're not pressing the up or down arrow keys. And here's the actual steering taking place. We didn't change any of that. That's pretty much it. And one more thing, in the camera follow, you may have noticed that the camera wasn't rotating exactly with the cart when I was turning left and right, and that's because this code only happens, transform that rotation equals continuing that slurp, the player's rotation and all that. It only happens if you're not gliding, as you can see by the exclamation mark in front of player script.glider fly. And if you are gliding, which is indicated by this else statement, then your rotation should equal to 0 on the x-axis, 0 on the z-axis, but it should still maintain the player's y rotation. And it gives you I give you a small explanation here with the comment. So if anyone reads this in the future with this project, it'll be easy to understand. And now let's check out what we have done. It should be the same as what I showed you before, unless I messed something up. I'm just gonna take a shortcut here because that's a long way. Okay, I'm just gonna. Okay, so here I'm gonna show you the gliding one more time. Yeah, so those angles, the angle variable was not really needed in the code over there. It does the same thing. And yeah, I guess this should complete the tutorial on my Kart-Controller for my Mario Kart game, because this is the basics of what I added in my Kart-Controller. There's a ton of extra stuff not related to the Kart-Controller or just maybe small refinements, but this is a basic skeleton of what it should be like. And yeah, I hope you guys enjoyed and learned something, and I hope this helped you. And thanks for watching, guys. Bye.